In this video, we are going to explore Enceladus, one of the most mysterious moons in the solar system. Space is filled with countless mysteries still waiting to be uncovered. If you're fascinated by space and physics, you're in the right place. Get ready as we drift into the mysterious world of Enceladus. Imagine water shooting 500 kilometers into space. Imagine geysers erupting from a world so cold that the surface temperature reaches minus 200 degrees. Imagine finding an ocean on a moon so tiny it could fit inside the borders of Texas. What you are seeing right now should not be happening. This is Enceladus, and it has completely changed everything we thought we knew about where life could exist in our solar system. For decades, we believed we understood moons. Moons were supposed to be dead. Moons were supposed to be frozen. Moons were supposed to be quiet, unchanging rocks orbiting their parent planets in eternal silence. But Enceladus refused to follow these rules. This tiny moon, barely visible as a speck of light from Earth, holds a secret that has turned the entire field of astrobiology upside down. And the most incredible part? That secret was hidden beneath kilometers of ice, waiting billions of years for us to discover it. Today, you are going to learn what we found beneath that ice and why it might be the most important discovery in the history of space exploration. So, what makes a moon special? Before we dive into the mystery of Enceladus, you need to understand just how common moons are in our solar system. Right now, astronomers have confirmed the existence of more than 200 moons orbiting the planets in our cosmic neighborhood. 200 worlds, each one circling its parent planet in an endless dance that has continued for billions of years. Our own moon, the one that lights up Earth's night sky, is just one member of this massive family. But here is the thing that most people do not realize about moons. The vast majority of them are completely unremarkable. They are cold. They are dead. They are essentially just rocks floating in space, their surfaces scarred by billions of years of asteroid impacts, their interiors frozen solid since the early days of the solar system. Take our own moon as an example. It is a grey, dusty, crater-covered ball of rock. Nothing moves there. Nothing changes there. Astronauts who visited the moon walked across surfaces that had remained untouched for billions of years, leaving footprints that will stay preserved in the lunar dust for millions of years to come, because there is no wind, no water, no geological activity to erase them. This is what astronomers expected to find when they looked at other moons throughout the solar system. They expected cold, dead, unchanging worlds where nothing had happened for billions of years. They expected surfaces covered in ancient craters, proof that these moons had been geologically inactive since the very beginning. They expected silence and stillness. And for most moons, this expectation turned out to be exactly correct. Most moons fit the pattern perfectly. They were frozen museums, preserving the early history of the solar system in their undisturbed surfaces. But Enceladus would prove to be completely different. This tiny moon was about to show us that our expectations about moons were dangerously limited. It was about to demonstrate that worlds we assumed were dead could be thriving with activity. It was about to reveal that the universe is far more surprising than we ever imagined. The story of Enceladus really begins in the early 1980s. This was an exciting time for planetary exploration. NASA had launched two ambitious spacecraft called Voyager 1 and Voyager 2, and these robot explorers were on a mission to visit the outer planets of our solar system, places that humans had never seen up close before. These spacecraft were equipped with cameras, instruments, and enough fuel to travel billions of kilometers from Earth. They were our eyes in the deep solar system, sending back images and data that would revolutionize our understanding of the outer planets. In November of 1980, Voyager 1 made its closest approach to Saturn. This giant planet, famous for its beautiful rings, had been observed through telescopes for centuries. But now we were finally going to see it in stunning detail. The spacecraft's cameras captured breathtaking images of Saturn's rings, revealing structures and patterns that no telescope on Earth could see. But Saturn itself was not the only target. The Voyager spacecraft were also programmed to observe Saturn's many moons, and that is when scientists got their first real look at Enceladus. What Voyager saw was unexpected. Among all of Saturn's moons, Enceladus appeared as an incredibly bright, white, shiny dot. In fact, when scientists analyzed the data, they discovered something remarkable. Enceladus reflected almost 100% of the sunlight that hit its surface. Think about what that means for a moment. Most objects in the solar system are dark and dull. They absorb sunlight. Rocky planets like Mars or Mercury reflect only a small fraction of the light that reaches them. Even Earth, with its bright clouds and oceans, reflects only about 30% of incoming sunlight. But Enceladus bounced back nearly all the light, making it the brightest known object in the entire solar system. This was a mystery. What could possibly make a moon's surface so incredibly bright and clean? Scientists knew that only fresh, pure ice could reflect light this effectively. But here was the puzzle that kept them awake at night. In space, moons get constantly bombarded by tiny dust particles, by radiation, by micrometeorites. Over millions of years, this bombardment should darken any surface, coating it in a layer of grime and debris. The surfaces of most moons are dark and dirty for exactly this reason. They have been sitting in space for billions of years, accumulating dust and damage. So why was Enceladus so impossibly clean? The only logical explanation was that something was actively renewing Enceladus's surface. Something was constantly laying down fresh layers of ice, covering up the old darkened material. But what could that something be? On a small distant moon that should be frozen solid, what process could be actively resurfacing the moon? Voyager 1 could not answer that question. Its brief flyby provided tantalizing clues, but no clear solutions. 9 months later, Voyager 2 also visited Saturn and took more pictures of Enceladus. But even with this additional data, the mystery remained unsolved. Scientists had to accept a frustrating reality. They had discovered something strange and wonderful, but they did not have the tools to understand it. They would have to wait. They would have to be patient. They would have to design a new mission, build new spacecraft, and send it on the long journey to Saturn. And that is exactly what they did. Planning a space mission is not like planning a road trip. You cannot just decide to go to Saturn and launch a spacecraft next week. Space missions require decades of preparation. First, scientists must convince governments to fund the mission, which means writing proposals, presenting evidence, and competing with hundreds of other worthy scientific projects for limited funding. Then, once approved, engineers must design and build spacecraft that can survive the harsh environment of space, travel billions of kilometers without breaking down, and operate autonomously because radio signals take so long to travel that real-time control from Earth is impossible. In the case of Saturn, NASA began planning a major new mission in the late 1980s. This mission would be called Cassini, named after the Italian astronomer Giovanni Cassini, who discovered several of Saturn's moons in the 17th century. But Cassini would not be going to Saturn alone. Attached to it was a smaller probe called Huygens, designed by the European Space Agency to land on Titan, Saturn's largest moon. Together, these two spacecraft represented the most ambitious mission to the outer solar system ever attempted. The design and construction of Cassini took years. Engineers had to solve countless technical problems. How do you power a spacecraft so far from the sun that solar panels become useless? They used radioactive plutonium to generate electricity. How do you ensure instruments can survive the frigid temperatures of the outer solar system? They designed elaborate heating systems and protective shields. How do you pack enough scientific instruments to study Saturn, its rings, its magnetic field, and its many moons? They carefully selected 12 different instruments, each designed to answer specific questions about the Saturn system. Finally, in October of 1997, Cassini launched from Cape Canaveral in Florida. But reaching Saturn would require 7 more years of travel. The spacecraft could not simply fly straight to its destination. Saturn is so far away, and the spacecraft needed to build up so much speed that the mission designers used a clever trick called gravity assists. Cassini flew past Venus twice, then past Earth once, then past Jupiter, using each planet's gravity to accelerate the spacecraft like a slingshot. This cosmic pinball game added years to the journey, but it was the only way to reach Saturn with the available rocket technology. Imagine the patience required. Scientists who were young graduate students when Cassini was first proposed were now middle-aged professors. Some researchers who helped plan the mission had retired or passed away before Cassini even arrived at Saturn. But in July of 2004, after traveling more than 3 billion kilometers, Cassini finally arrived at Saturn and fired its main engine to slow down and enter orbit around the ringed planet. The wait was over. The real exploration was about to begin. Cassini spent its first months at Saturn studying the planet itself and its magnificent ring system. But mission planners had not forgotten about Enceladus. That bright, mysterious moon had been a target of interest since the Voyager flybys decades earlier. Scientists were eager to get a closer look, to see if they could solve the puzzle of its impossibly clean surface. So in February of 2005, Cassini was commanded to alter its orbit and make a relatively close flyby of Enceladus, passing within about 1,000 kilometers of the Moon's surface. The spacecraft's cameras began taking pictures as it approached. Scientists back on Earth waited anxiously for the images to arrive, transmitted across more than 1 billion kilometers of space at the speed of light, which meant even moving at the fastest speed in the universe. The signal took more than an hour to reach Earth. When the images finally appeared on their computer screens, scientists could barely believe what they were seeing. The south pole of Enceladus was not like the rest of the Moon. While most of the surface was smooth and bright, the south pole showed something completely unexpected. There were massive plumes, like geysers, shooting upward from the surface. But these were not small features. These jets of material were erupting with such force that they were spraying material 500 kilometers into space, more than the entire diameter of the Moon itself. Imagine standing on Earth and seeing geysers shooting high enough to reach the International Space Station. That is the scale of what Cassini was observing on Enceladus. The reaction in the mission control room was a mixture of shock, confusion, and pure scientific excitement. Some scientists literally stood up from their chairs, pointing at the screens, asking their colleagues if they were seeing the same thing. Others immediately started checking the instruments, wondering if there was some kind of malfunction producing false data. But as more images came in, as more instruments confirmed the readings, the reality became undeniable. Enceladus was active. This tiny moon, which should have been frozen dead for billions of years, was erupting like a cosmic geyser, spraying material into space right now. But what exactly was being sprayed out? The first clues suggested it was water. Water vapor, to be precise, mixed with tiny particles of ice. The spacecraft's instruments detected the characteristic signatures of H2O molecules in the plume. This meant that somewhere beneath the icy surface of Enceladus there was liquid water. Liquid water on a moon where the surface temperature never rose above -200 degrees Celsius. Liquid water on a world so small it should not have enough internal heat to melt anything. Liquid water being shot into space with enough force to escape the Moon's weak gravity. This discovery raised more questions than it answered. Where was this water coming from? What was providing the energy to keep it liquid? How long had this been going on? Was there an underground lake, or something even more substantial? Scientists knew they had stumbled onto something extraordinary, but they also knew they needed more data, more flybys, more time to unravel this mystery. The hunt for answers was just beginning, and Enceladus had just become the most fascinating moon in the solar system. Now that scientists knew Enceladus was actively erupting water into space, they faced a fundamental problem. This activity should not be possible. To understand why, you need to grasp some basic physics about heat, size, and how objects cool down in space. Do not worry, we will keep this simple, but understanding this problem is crucial to appreciating just how remarkable Enceladus truly is. Think about making a cup of hot tea. If you pour hot water into a large teapot, it stays warm for quite a long time. But if you pour that same hot water into a tiny espresso cup, it cools down much faster. This happens because the small cup has more surface area compared to its volume, which means heat escapes more quickly. The same principle applies to moons and planets in space. Large worlds like Earth can hold on to their internal heat for billions of years. Small worlds cool down quickly and freeze solid. Enceladus is tiny. At just 504 kilometers across, it is smaller than the state of Texas. You could fit more than 50 Enceladuses inside Earth. When you calculate the volume of Enceladus compared to its surface area, the numbers tell a clear story. This moon should have lost all its internal heat billions of years ago. It should be frozen completely solid, through and through from its core to its surface. There should be no liquid water. There should be no geological activity. There should be no geysers. And yet there it was, defying all expectations, shooting water hundreds of kilometers into space. So where was the energy coming from? This was the puzzle that consumed scientists. On Earth, we have internal heat left over from the planet's formation, plus additional heat generated by radioactive decay of elements like uranium and thorium deep in Earth's core. This heat drives plate tectonics, volcanoes, and all the geological activity we see. But Enceladus is too small to have retained significant formation heat, and too small to have enough radioactive elements to generate the energy needed to maintain an active geology. The answer had to be something else, something external, something that was continuously pumping energy into this little moon. And scientists believed they knew what that something was. It was Saturn itself. But understanding how Saturn could heat up a moon required understanding one of the most beautiful and powerful forces in the solar system. It required understanding tides, not the ocean tides we see on Earth, but gravitational tides that can literally squeeze and stretch entire worlds. After the initial discovery in 2005, Cassini mission planners made a bold decision. They would send the spacecraft directly through the plumes of Enceladus. This was not without risk. Flying through a cloud of ice particles at high speed could potentially damage the spacecraft's sensitive instruments. But the scientific reward was too great to pass up. If Cassini could sample the material in the plumes, it could directly analyze what was coming from inside Enceladus. It would be like getting a free sample of the moon's interior without having to drill through kilometers of ice. Starting in 2008, Cassini began a series of daring flybys, some passing as close as 25 kilometers above Enceladus's surface, flying directly through the densest parts of the plumes. The spacecraft's instruments worked frantically during these brief encounters, analyzing the composition of the ice particles and vapor, measuring temperatures, recording data as fast as possible. Each flyby lasted only minutes, but those minutes were packed with scientific treasure. What Cassini found in those plumes was astonishing. First, yes, it was definitely water, lots and lots of water vapor mixed with tiny ice crystals. But it was not just pure water. The instruments detected something else mixed in with the water. Salt, sodium chloride, table salt. The same chemical that flavors your French fries was flying through space above Enceladus. This might seem like a small detail, but to scientists this was huge. Salt in the water meant this was not just melted ice from near the surface. This was water that had been in contact with rocks, dissolving minerals from a rocky core, becoming salty just like Earth's oceans. But the discoveries did not stop there. As Cassini flew through the plumes again and again during subsequent years, more sophisticated instruments came online and analyzed the samples in greater detail. They found organic molecules. These are molecules that contain carbon bonded with other elements, the basic building blocks of life as we know it. Now, it is critical to understand that organic molecules do not mean life. They are simply carbon-based chemicals, and they can form through completely non-biological processes. But their presence was significant because life requires organic molecules. Finding them on Enceladus meant that at least one of the key ingredients for life was present. The instruments detected methane, propane, ethane, and other simple organic compounds. Then, in later flybys, they found even larger, more complex organic molecules, some with chains of carbon atoms bonded together in ways that began to resemble the kinds of molecules that life on Earth uses. Each discovery made the scientific community more and more excited because the evidence was building towards something incredible. Then came perhaps the most important discovery of all. In 2017, scientists analyzing data from Cassini's plume dives announced they had detected molecular hydrogen gas, H2. To most people, this might seem less exciting than finding organic molecules, but to scientists searching for life, this was the game changer. Let me explain why. Hydrogen gas in the plumes meant that chemical reactions were happening inside Enceladus. Specifically, it suggested that hot water was reacting with rocks on the ocean floor, a process that produces hydrogen as a byproduct. This process, called serpentinization, happens on Earth at deep ocean hydrothermal vents, those hot springs on the seafloor where superheated water meets volcanic rock. And here is the truly mind-blowing part. On Earth, those hydrothermal vents support entire ecosystems of life that do not need sunlight. Microbes there use the hydrogen as an energy source, combining it with carbon dioxide to produce methane and extract energy. If the same process was happening on Enceladus, it meant the Moon had a potential energy source for life. Let that sink in for a moment. Cassini had found water, salt, organic molecules, and an energy source. These are the fundamental ingredients that life needs, all of them, together, on a tiny moon orbiting Saturn. With all this evidence from the plumes, scientists began to piece together what must be happening beneath the ice. There had to be a reservoir of liquid water down there. But how big was it? Was it just a small underground lake near the South Pole? Or was it something more substantial? To answer this question, scientists turned to gravity. Yes, gravity. Even though Enceladus is small, it still has gravity, and that gravity pulls on Cassini as the spacecraft flies past. By very precisely measuring how much Cassini's trajectory gets bent as it passes Enceladus, scientists can calculate the Moon's mass and how that mass is distributed. It is like being able to weigh different parts of the Moon and figure out what they are made of without ever seeing inside. The gravity measurements told a surprising story. The interior of Enceladus was less dense than it would be if the Moon was solid ice all the way through. Something less dense than ice was inside. And the only thing less dense than ice that makes sense in this environment is liquid water. Liquid water is slightly less dense than frozen ice, which is why ice cubes float in your drink. The gravity data suggested there was a significant amount of liquid water inside Enceladus. But scientists needed more evidence. They got it by studying how Enceladus wobbles. Just like a spinning top does not spin perfectly smoothly, Enceladus does not orbit Saturn in a perfectly rigid way. It wobbles slightly, and the amount of wobble depends on whether the interior is solid or liquid. A solid moon wobbles differently than a moon with liquid sloshing around inside. By carefully measuring Enceladus's rotation over many years of observations, scientists determined that the moon was wobbling more than it should if it was solid. This confirmed it. There was liquid inside. Putting all the evidence together, scientists reached a stunning conclusion. Enceladus does not just have a small underground lake. It has a global ocean. An ocean that stretches under the entire icy shell, surrounding the rocky core, reaching from pole to pole. This ocean is buried beneath 20 to 30 kilometers of ice at most locations, a bit thinner at the South Pole where the geysers erupt. And this ocean is deep. Scientists estimate it is about 10 kilometers deep, which might not sound like much compared to Earth's oceans, but remember, Enceladus is a tiny moon. That 10-kilometer deep ocean wrapping around the entire moon contains a massive amount of water. Think about it this way. The volume of water in Enceladus's ocean is comparable to some of the largest lakes on Earth. It is more water than in Lake Superior or Lake Baikal. This tiny moon, this little white speck orbiting Saturn, contains an entire ocean world hidden beneath its ice. And unlike the dry, dead surface, that ocean is in direct contact with the rocky sea floor, where water and rock interact, where chemical reactions happen, where energy flows. This hidden ocean represented one of the most profound discoveries in the history of planetary science, because it meant that habitable environments might exist in places we never thought to look. Now we need to talk about one of the most bizarre features of Enceladus. The geysers do not erupt randomly from the surface. They all come from very specific locations on the South Pole. And these locations are marked by 4 strange parallel cracks in the ice that scientists nicknamed the tiger stripes. These are officially called sulci, which is a geological term for grooves, and each one has been given a name. There is Alexandria sulcus, Cairo sulcus, Baghdad sulcus, and Damascus sulcus. But everyone calls them the tiger stripes because when you look at pictures of the South Pole, these 4 parallel cracks look exactly like the stripes on a tiger's back. Each tiger stripe is about 130 kilometers long, about 2 kilometers wide, and the 4 stripes are roughly parallel to each other, spaced several kilometers apart. When Cassini flew close to these features, its infrared instruments detected something remarkable. These tiger stripes were warm. Not hot like a volcano, but significantly warmer than the surrounding ice. While the average surface temperature on Enceladus hovers around -200 degrees Celsius, the tiger stripes measured closer to -130 degrees. That is still incredibly cold by Earth standards, but it is about 70 degrees warmer than it should be, and in the frigid environment of Enceladus, that difference is huge. The tiger stripes are where the geysers erupt from. High-resolution images show dozens of individual jets shooting out from along these cracks like a row of fire hoses pointing upward. But why 4 parallel stripes? Why are they only at the South Pole? Why are they arranged in this peculiar pattern? These questions puzzled scientists for years. The answer involves understanding how Saturn's gravity affects Enceladus. You see, Enceladus does not orbit Saturn in a perfect circle. Its orbit is slightly elliptical, slightly egg-shaped. This means that as Enceladus travels around Saturn, the distance between the two bodies changes. Sometimes Enceladus is a little bit closer to Saturn, sometimes a little bit farther away. And because gravity gets stronger with proximity, this means Saturn's gravitational pull on Enceladus is constantly changing as the Moon orbits. Think of it like this. Imagine holding a rubber ball in your hand and squeezing it, then releasing, then squeezing again, then releasing, over and over. That is essentially what Saturn is doing to Enceladus. As the Moon gets closer to Saturn, the gravity gets stronger and squeezes the Moon. As it moves farther away, the gravity weakens and the Moon relaxes. This constant squeezing and releasing is called tidal flexing, and it generates heat through friction, just like bending a paperclip back and forth repeatedly makes it hot. The tidal heating is strongest at certain points on the Moon, and computer models suggest that the South Pole region experiences particularly strong tidal stresses. The 4 tiger stripes seem to be the places where these tidal forces have cracked open the ice shell, creating pathways for the pressurized ocean water below to escape upward. The heat from tidal friction keeps these cracks from freezing shut, allows water to remain liquid even as it rises through the cold ice, and provides the energy to blast the water into space as dramatic geysers. But there is still one piece of this puzzle that makes the system even more fascinating. Enceladus's slightly elliptical orbit is not random. It is maintained by another moon. Enceladus orbits Saturn exactly twice for every one orbit completed by another moon called Dione. This is called an orbital resonance, and it is like 2 dancers moving in perfect synchronization. Every time Enceladus completes 2 orbits around Saturn, Dione completes 1, and when they align, Dione's gravity gives Enceladus a little gravitational tug. These repeated tugs prevent Enceladus's orbit from becoming circular, keeping it slightly elliptical, which means the tidal heating continues generation after generation. So the tiger stripes, the geysers, the ocean, the energy, all of it exists because of a cosmic dance between Enceladus, Dione, and Saturn. Remove any piece of this system and Enceladus would be dead and frozen. But with all the pieces in place, this tiny moon becomes a thriving world with an underground ocean and spectacular ice geysers announcing its presence to the cosmos. Before we can evaluate whether Enceladus might host life, we need to understand what life actually requires. This is a fundamental question in astrobiology, and fortunately the answer is relatively simple because we have one very good example to study. Earth. Life on Earth in all its incredible diversity, from bacteria to blue whales, from mushrooms to humans, all shares certain basic requirements. By studying what life needs here, we can make educated guesses about what life would need anywhere in the universe. Scientists have identified 3 fundamental requirements for life as we know it. First, liquid water. Second, organic molecules, the chemical building blocks. Third, an energy source. Let me explain each of these in simple terms so you can understand why they matter so much. Liquid water is crucial because life needs a solvent, a liquid medium where chemical reactions can happen. On Earth, every living cell is mostly water. Water dissolves nutrients, carries away waste, allows molecules to bump into each other and react. You might wonder if life could use a different liquid instead of water. Could something live in liquid methane or liquid ammonia? Perhaps, and scientists have speculated about such exotic possibilities. But water has unique properties that make it especially good for life. It is stable across a wide range of temperatures, it can dissolve both polar and non-polar molecules, and it is incredibly common in the universe. So when scientists search for life elsewhere, they follow the water. No liquid water means no life as we understand it. Organic molecules are the second requirement. These are molecules built around carbon atoms bonded to other elements like hydrogen, oxygen, nitrogen and sulfur. Why carbon? Because carbon atoms can form 4 chemical bonds, allowing them to link together into chains, rings and complex 3-dimensional structures. This versatility makes carbon perfect for building the complicated molecules that life requires, molecules like proteins, DNA, carbohydrates and fats. Without organic molecules, there is nothing to build life from. You need these carbon-based building blocks to construct the machinery of living cells. The third requirement is energy. Life is not a static thing. Living organisms must constantly work to maintain themselves, to grow, to reproduce. This work requires energy. On Earth, most of that energy ultimately comes from the sun. Plants capture sunlight through photosynthesis and convert it into chemical energy stored in sugars. Animals eat plants or eat other animals that ate plants, passing that solar energy up the food chain. But the sun is not the only possible energy source for life. Deep in Earth's oceans, where sunlight never reaches, there are entire ecosystems powered by chemistry instead of light. Microbes at hydrothermal vents extract energy from chemicals dissolved in the hot water, particularly hydrogen and hydrogen sulfide, combining them with oxygen or other molecules in reactions that release energy. These microbes prove that life does not need sunlight. It just needs some reliable source of energy. So those are the three requirements: water, organic molecules, energy. Scientists sometimes call these the ingredients for habitability. Any place in the universe that has all three ingredients is potentially habitable, meaning life could theoretically exist there even if it does not actually exist. Finding a habitable environment does not guarantee life, but it at least makes life possible. And this is exactly the checklist that scientists began applying to Enceladus after Cassini's discoveries. Does this moon have liquid water? Check. Does it have organic molecules? Let us investigate. Does it have an energy source? Let us find out. Each answer would bring us closer to understanding whether Enceladus is not just an interesting moon, but a potentially living world. We already mentioned that Cassini detected organic molecules in the plumes shooting from Enceladus, but now we need to dive deeper into what that actually means and why it got scientists so excited. Remember, the term organic does not mean alive or even biological. It simply means carbon-based. Organic molecules can form through completely ordinary chemical processes that have nothing to do with life. So finding organic molecules on Enceladus does not prove life exists there. But it does prove that one of the key requirements for life is present. The first organic molecules Cassini detected were relatively simple. Methane, which is just one carbon atom bonded to 4 hydrogen atoms. Propane, which is 3 carbon atoms in a row with hydrogen atoms attached. Ethane, which is 2 carbon atoms bonded together with hydrogen atoms. These are the same chemicals that fuel your barbecue grill and camp stoves. They are hydrocarbons, the simplest possible organic compounds. Finding these on Enceladus was interesting because it meant carbon and hydrogen were combining in the subsurface ocean. But these simple molecules do not tell us much about the potential for life. They are just too basic. But as Cassini continued its mission and flew through the plumes more times with more sensitive instruments, scientists began detecting larger, more complex organic molecules. They found molecules with longer carbon chains, molecules with carbon rings, molecules with nitrogen and oxygen atoms incorporated into their structures. In 2018, scientists analyzing data from Cassini's final plume dives reported finding fragments of molecules that were large enough and complex enough to be called macromolecular organic compounds. These are big molecules, not quite as large as the proteins or DNA in living cells, but getting closer to that level of complexity. The presence of these larger organic molecules was significant for several reasons. First, it suggested that organic chemistry on Enceladus was not limited to simple reactions. Something was allowing carbon atoms to link together into bigger structures. Second, some of these molecules contained functional groups, specific arrangements of atoms like carboxyl groups or amino groups that are found in biologically important molecules on Earth. Again, this does not mean life exists on Enceladus. These structures can form without biology. But it means the chemical environment on Enceladus is capable of producing the kinds of molecules that could serve as building blocks for life. Think of it this way. Imagine you are trying to determine if a particular location could support a bakery. You would not need to find actual bread to know it was possible. You would just need to find flour, water, yeast, and salt. The presence of these ingredients proves that bread could be made, even if nobody is making it yet. The organic molecules on Enceladus are like those baking ingredients. They prove that the chemical building blocks of life are available. Whether anything is actually using those building blocks to build life remains an open question. But at least we know the ingredients are there. Scientists also learned something important by studying where these organic molecules came from. Some could have been produced by simple chemical reactions in the ice, but the larger, more complex molecules almost certainly came from the ocean itself, where water and rock interact at the seafloor, where temperatures and pressures allow more elaborate chemistry to occur. This meant that the ocean of Enceladus was not just a sterile bath of water. It was a chemically active environment where carbon-based molecules were being synthesized, broken apart, and reformed in an ongoing cycle of chemistry that, on Earth, would be considered a sign of a vibrant chemical environment ripe for the emergence of life. The detection of molecular hydrogen in Enceladus's plumes might have seemed like a minor detail compared to finding organic molecules, but to scientists hunting for life, this was the most important discovery of all. To understand why, we need to talk about what energy means in the context of life and chemistry. When scientists talk about an energy source for life, they are talking about chemical reactions that release energy that organisms can capture and use. On Earth, we are most familiar with reactions involving oxygen. When you burn wood, when your cells break down glucose, when a car engine burns gasoline, all these processes involve combining something with oxygen, and these reactions release energy. But oxygen is not required for energy-producing reactions. There are many other chemical reactions that release energy, and hydrogen is involved in some of the most important ones for life. The hydrogen molecules that Cassini detected in the plumes were not just floating around randomly. They were the product of chemical reactions happening deep inside Enceladus. Specifically, they were produced by a process called serpentinization, which is a complicated word for a relatively simple concept. When hot water comes into contact with certain types of rock, particularly rocks rich in iron and magnesium like olivine and pyroxene, a chemical reaction occurs. The water reacts with the iron in the rock, oxidizing it, and in the process, hydrogen gas is released. This is the same process that occurs at hydrothermal vents on Earth's ocean floor. Hot water percolates down through cracks in the seafloor, gets heated by magma below, reacts with the rock, and comes back up enriched with hydrogen, dissolved metals, and other chemicals. When this hydrogen-rich hot water mixes with the cold seawater, it creates a chemical disequilibrium, meaning it creates an environment where different chemicals that want to react with each other are brought together. And this disequilibrium is what powers life at those vents. On Earth, certain microbes have evolved to take advantage of this hydrogen. They are called methanogens, and they combine hydrogen with carbon dioxide to produce methane, releasing energy in the process. These microbes do not need sunlight, they do not need oxygen, they do not need any connection to the surface world at all. They live in total darkness, in crushing pressure, at temperatures that would boil water, and they thrive because they can extract energy from the simple chemical reaction of combining hydrogen with carbon dioxide. The discovery of hydrogen on Enceladus meant that the same process was likely happening there. Deep below the ice, where the ocean meets the rocky core, hot water was reacting with rock, producing hydrogen. That hydrogen was dissolving into the ocean water, creating the same kind of chemical disequilibrium that powers life at Earth's hydrothermal vents. If microbes like Earth's methanogens existed on Enceladus, they would have everything they need: water to live in, hydrogen as an energy source, carbon dioxide and organic molecules as building blocks. They could exist in the eternal night of Enceladus's hidden ocean, never seeing the sun, never knowing that a rocky planet called Earth existed, living their entire existence in the dark, warm, chemical-rich environment of their underwater world. The beauty of this energy source is that it is sustainable. The hydrogen is being continuously produced as long as the ocean remains liquid and in contact with the rocky core. Tidal heating from Saturn keeps the ocean from freezing. The orbital resonance with Dione keeps the tidal heating going. The system is stable and could potentially continue for billions of years. This means that if life emerged on Enceladus at some point in the past, it could have had billions of years to evolve, to diversify, to adapt to its environment. Time is one of the most important ingredients for life, and Enceladus has had plenty of it. Now comes the most exciting part of our story, and also the most speculative. Let me be absolutely clear about something first. We have not found life on Enceladus. Cassini did not detect any living organisms. No cells, no DNA, no definitive biosignatures. Everything I'm about to describe is theoretical, based on what we know about life on Earth and how it might adapt to environments similar to Enceladus. But the fact that we can even have this conversation, that we can seriously discuss what life might be like on an alien ocean world, is itself a testament to how profound the Cassini discoveries were. So what could be living in Enceladus's ocean? Let us start by thinking about the environment. It is completely dark. No sunlight penetrates 20 kilometers of ice. The ocean is cold by Earth standards, probably near freezing point of water, maybe a bit warmer near hydrothermal vents, if they exist. The pressure is significant but not crushing, equivalent to the pressure in Earth's oceans at moderate depths. The water is salty. There are organic molecules floating around. There are minerals dissolved from the rocky core. And there is hydrogen available as an energy source. On Earth, we have microbes that live in remarkably similar conditions. They are called extremophiles, meaning they love extreme environments. Let me tell you about a few types that could, in theory, survive on Enceladus. First, there are methanogens, which I mentioned earlier. These are a type of archaea, a domain of life separate from bacteria. Methanogens are anaerobes, meaning they do not need oxygen. They live in places like deep ocean sediments, underwater hot springs, and even in the digestive systems of cows and termites. They take hydrogen and carbon dioxide and combine them to make methane, extracting energy from this reaction. If methanogens or something like them exist on Enceladus, they would be perfectly happy living in the dark ocean, clustering around hydrothermal vents where hydrogen is most concentrated, slowly metabolizing and growing. Second, there are chemosynthetic bacteria. These microbes also do not need sunlight. Instead, they extract energy from chemical reactions involving sulfur compounds, iron, or other elements. Some of them oxidize hydrogen sulfide, producing sulfur as a waste product. Others oxidize iron or manganese. At Earth's hydrothermal vents, these chemosynthetic bacteria form the base of entire ecosystems. They are the primary producers, like plants are on land, converting chemical energy into biological tissue that other organisms can eat. If Enceladus has hydrothermal vents, similar chemosynthetic microbes could potentially exist there. Third, there are psychrophiles, which means cold-loving organisms. These microbes are adapted to live in extremely cold environments, places where most life would freeze to death. They have special proteins and cell membranes that remain flexible at temperatures near or below freezing. They grow slowly because chemical reactions happen more slowly in the cold, but they can survive and reproduce. Some psychrophiles on Earth live in Antarctic ice, in Arctic ocean water, and in glaciers. The cold ocean of Enceladus would not be a problem for these microbes. They are built for it. Now, combining these characteristics, imagine a microbe that is psychrophilic, chemosynthetic, and capable of using hydrogen as an energy source. Such an organism would be perfectly adapted to Enceladus. It could live in the cold, dark ocean. It could extract energy from the hydrogen produced by water rock reactions. It could use the organic molecules present in the ocean as carbon sources. It would not need anything from the surface, nothing from the sun, nothing from the outside universe. It would be entirely self-sufficient in its hidden underwater realm. But could life on Enceladus be more than just microbes? Could there be larger organisms, complex life, maybe even something we would recognize as animal-like? This is where speculation becomes even more uncertain, but let us think it through. On Earth, everywhere there are microbes at the bottom of a food chain, other organisms have evolved to eat those microbes. At hydrothermal vents, there are tube worms, clams, crabs, shrimp, and fish, all ultimately dependent on the chemosynthetic bacteria. Could something similar happen on Enceladus? The challenge is energy. Life gets more complex when there is more energy available. Earth's surface is flooded with sunlight, providing enormous amounts of energy that plants can capture and pass up the food chain. This energy abundance allows for large animals, fast movement, complex behaviors. But on Enceladus, the energy from hydrogen-based chemistry is much more limited. There is enough to support microbes, probably enough to support simple ecosystems, but probably not enough to support large active animals like we have on Earth. That said, if life has been evolving on Enceladus for billions of years, who knows what strange and wonderful forms it might have taken. Life on Earth has shown itself to be incredibly creative in finding ways to survive and thrive. Perhaps Enceladian life has evolved strategies we cannot imagine, ways of extracting energy or organizing themselves that we have not thought of. Perhaps the ocean is teeming with microbial life so abundant that it forms visible mats or films on the ocean floor. Perhaps simple multicellular organisms have evolved, slow-moving filter feeders that drift in the currents, straining microbes from the water. Perhaps nothing lives there at all, and the ocean is sterile, despite having all the right ingredients. This is the beautiful uncertainty of science. We have enough information to know that life is possible on Enceladus. We do not yet have enough information to know if it actually exists. And that uncertainty is what drives us forward, what makes us want to send another mission, to sample the plumes more carefully, to maybe one day send a probe that could melt through the ice and explore the ocean directly. Because the answer, whatever it is, will be profound. Think of every ice grain shooting out from Enceladus's plumes as a tiny message from the hidden ocean below. Each grain is a frozen droplet of ocean water, launched into space, still carrying traces of whatever was dissolved in it. Whatever chemicals and molecules were present in the deep ocean before the water erupted. Scientists have learned to read these tiny messengers like detectives examining evidence at a crime scene, and the story they tell is fascinating. When water erupts through the tiger stripes, it gets flash frozen almost instantly in the extreme cold of space. This rapid freezing traps everything that was in the water at the moment of eruption. Salt crystals, organic molecules, bits of rock, microscopic particles all get locked into the ice grains. As these grains fly upward through the plumes, some fall back to Enceladus's surface, continuously resurfacing the moon and keeping it bright white. Others achieve enough velocity to escape Enceladus's weak gravity and spread out into space, forming a faint ring around Saturn called the E-ring. And some, crucially for our story, happen to be in the exact right place at the exact right time when Cassini flew through. Cassini's instruments could analyze individual ice grains as they hit the spacecraft. Think about the precision required here. These grains are tiny, often just a few microns across, smaller than the width of a human hair. The spacecraft is moving at several kilometers per second relative to Enceladus. And yet, instruments aboard Cassini could capture these grains, measure their size, determine their composition, identify what chemicals were locked inside them, all in the fraction of a second before the grain was destroyed by the impact. The size distribution of the ice grains told scientists about the force of the eruptions. Larger grains are heavier and harder to accelerate, so their presence high in the plumes meant the eruptions were powerful. Smaller grains are easily carried upward by vapor pressure. By analyzing the full range of sizes, scientists could estimate the pressure of the water beneath the tiger stripes, how fast it was moving, how much turbulence was involved. They could essentially reconstruct the journey each droplet took from the ocean to space. The composition of the grains revealed even more. Remember the salt we mentioned earlier? By measuring how much salt was in the ice grains, scientists could calculate the salinity of Enceladus's ocean. It turned out to be remarkably similar to Earth's oceans, with a salt concentration that would make the water taste salty but still be less salty than the Dead Sea. This tells us that the ocean has been in contact with rocky material for a long time, dissolving minerals and building up salt content, just like Earth's oceans did billions of years ago when water first condensed on our planet and began weathering rocks. But different ice grains had different compositions, and this told its own story. Some grains were relatively pure water ice with just a bit of salt. Others were packed with organic molecules. Some contained tiny particles of silica, which is silicon dioxide, the same material that makes up sand and quartz. These silica particles were especially telling. Silica nanoparticles like those found in the plumes typically form when hot water dissolves silica from rocks and then rapidly cools, causing the silica to precipitate out as tiny particles. On Earth, this happens at hydrothermal vents. Finding it on Enceladus was yet another piece of evidence suggesting that hot springs existed on the ocean floor. Every flyby through the plumes gave scientists more data points, more ice grains to analyze, more pieces of the puzzle. Over the years of Cassini's mission, scientists built up a detailed chemical portrait of Enceladus's ocean. They knew it was salty. They knew it contained organic molecules of various sizes and complexities. They knew it had dissolved silica. They knew it had hydrogen. They knew it had carbon dioxide and methane. They even detected traces of ammonia, which is interesting because ammonia could act as antifreeze, lowering the freezing point of water and allowing liquid water to exist at even colder temperatures than normal. By comparing the composition of Enceladus's ocean with Earth's oceans, scientists found remarkable similarities. Yes, there were differences. Enceladus's ocean is colder and may have different dissolved minerals. But the basic chemistry, the presence of salt, organics, and dissolved gases, the pH level estimated from the types of molecules present, all pointed to an ocean that was not radically alien. It was an ocean that Earth-like life could potentially recognize as a suitable home. One of the most important questions about Enceladus is how long has this been going on? Has the ocean existed for millions of years, billions of years, or did it only recently become liquid? This matters enormously when we think about the possibility of life, because life, at least life as we know it on Earth, takes a long time to evolve. On Earth, life appeared relatively quickly after conditions became suitable. Once the surface cooled enough for liquid water to exist, once the bombardment from space debris calmed down, microbial life emerged within a few 100 million years. But that was simple life, single-celled organisms with no nucleus. It took nearly 2 billion more years for more complex cells to evolve, cells with nuclei and mitochondria like the cells in your body. And it took another billion years after that for multicellular life to emerge. If we want to find life on Enceladus, we need to know if it has had enough time to evolve. Looking at the surface of Enceladus gives us important clues. As I mentioned earlier, the surface is remarkably smooth and bright, with very few impact craters. This is significant because everywhere else in the solar system, objects accumulate craters over time. The Moon is covered in craters. Mars is covered in craters. Even young surfaces on Earth show impact scars if you look in the right places. Craters are like a clock that tells us how old a surface is. More craters means older surface. Fewer craters means younger surface, or a surface that gets resurfaced frequently. Enceladus has almost no old craters on its south polar region, and even the rest of the surface has far fewer craters than it should if the surface was billions of years old. Scientists estimate that the surface is geologically young, perhaps only a few 100 million years old in places, maybe even younger near the tiger stripes, where active resurfacing is happening right now. But young surface age does not mean the ocean is young. It just means the surface gets paved over with fresh ice frequently. To understand the age of the ocean itself, scientists looked at other evidence. Orbital mechanics tell us that the resonance between Enceladus and Dione, the thing that keeps Enceladus's orbit elliptical and enables tidal heating, is probably a long-term stable arrangement. Computer simulations suggest this configuration could persist for billions of years. This is good news for the possibility of ancient life, because it means the energy source powering Enceladus's ocean could have been operating since very early in the solar system's history. Chemical evidence also suggests longevity. The amount of salt in the ocean and the presence of certain dissolved minerals indicate that water has been in contact with rock for a long time, slowly dissolving minerals and building up the current chemistry. If the ocean had only existed for 1 million years, we would not expect to see the level of dissolved material that Cassini detected. The ocean appears to be mature, chemically equilibrated, suggesting it has been liquid for many millions and possibly billions of years. Scientists have also considered whether Enceladus's activity could be cyclical. Maybe the ocean freezes and thaws over millions of years, active for a while, then dormant, then active again. This is possible, and it would complicate the question of whether life could evolve and persist. If the ocean freezes completely every few million years, any life would have to survive these deep freeze events, which is challenging, though not impossible. Some microbes on Earth can survive being frozen for thousands or even millions of years in a dormant state. But continuous liquid water would be better for life, giving it uninterrupted time to evolve and diversify. The current scientific consensus is that Enceladus's ocean has probably been liquid for at least hundreds of millions of years, possibly much longer, potentially dating back billions of years to the early solar system. If this is true, if the ocean has been liquid and chemically active for that long, then it has had enough time for life to potentially emerge, enough time for that life to potentially adapt to its environment, enough time for us to hope that when we go back and look more carefully, we might find something alive. We cannot see through the ice to directly observe the ocean floor of Enceladus, which is frustrating because the ocean floor is probably where the most interesting things are happening. But scientists have clever ways of figuring out what must be down there without actually seeing it. It is like being a detective who reconstructs a room just from footprints and fingerprints without ever opening the door. Gravity data from Cassini provided the first clues. By measuring how Enceladus's gravity affected the spacecraft's trajectory, scientists could calculate not just that there was less dense material inside, indicating an ocean, but also the approximate thickness of that ocean and what must lie below it. The calculations indicated that beneath the ocean there must be a core made of rock, probably similar to rocky material found throughout the inner solar system. This core is estimated to be roughly 300 to 400 kilometers in diameter, with the ocean wrapping around it and the ice shell encasing everything. But knowing there is a rocky core and knowing what is happening on that core are different questions. This is where chemistry becomes our detective tool. Remember those silica nanoparticles found in the ice grains? On Earth, those form when hot water reacts with silica-rich rocks and then cools rapidly. For this to happen on Enceladus, the ocean floor must have exposed rock that water can interact with. And there must be hot spots where water is heated by geological activity, either by tidal heating directly or by radioactive decay in the rocky core. The presence of hydrogen in the plumes tells us even more about the ocean floor. Hydrogen production through serpentinization requires water to react with iron-rich rocks. This means the ocean floor must be made of, or at least include, rocks that contain iron and magnesium. Rocks like olivine and pyroxene that are common in the mantles of rocky planets. It also means these rocks must be exposed to water, not covered by thick layers of sediment or other material that would prevent the water-rock reactions. Scientists have built computer models to simulate what the ocean floor might look like. Imagine a landscape of rocky hills and valleys, covered in a thin layer of sediment made from silica particles, salt crystals, and organic material that has settled down from the water above. In some places, especially where tidal heating is strongest, perhaps near the South Pole region where the tiger stripes are located above, there might be cracks in the ocean floor where water seeps down into the rocky core, gets heated, reacts with the rocks, and then rises back up enriched with hydrogen, metals, and other dissolved chemicals. These rising plumes of hot water would create hydrothermal vents, underwater chimneys built from minerals that precipitate out when the hot water meets the cold ocean. Around these vents, the conditions would be perfect for life. Warm water, abundant chemicals, energy from chemical reactions, and organic molecules floating in from the surrounding ocean. If life exists on Enceladus, this is where we would most expect to find it, clustered around these deep ocean hot springs, far from the frozen surface, in the warm, chemical-rich water. Of course, all of this is theoretical. We have never directly observed the ocean floor of Enceladus. We have never seen a hydrothermal vent there. We are inferring all of this from indirect evidence, from chemistry and physics and comparisons to Earth. But the beautiful thing about science is that these inferences are testable. We can design missions to gather more data, to look more carefully, to eventually confirm or refute these models. And that brings us to one final piece of the detective work, understanding how everything connects. Throughout this story, I have mentioned Saturn many times, but now we need to really understand and appreciate just how essential Saturn is to making Enceladus work. Without Saturn, Enceladus would be nothing but a frozen ball of ice, as dead as most other moons in the solar system. It is Saturn's presence, Saturn's massive gravity, and Saturn's entire system of moons that creates the conditions for Enceladus to be an active, potentially habitable world. Let us start with the basics. Saturn is huge. It is the second largest planet in the solar system after Jupiter, with a mass 95 times greater than Earth. All that mass creates powerful gravitational fields that dominate everything in the region. Enceladus is just a tiny speck compared to Saturn, and it orbits relatively close to the planet, only about 240,000 kilometers from Saturn's center. At this distance, Saturn's tidal forces on Enceladus are significant. Tidal forces are what happen when different parts of an object experience different strengths of gravity. The side of Enceladus facing Saturn feels stronger gravity than the side facing away from Saturn because it is closer. This difference in gravitational pull creates a stretching effect, like two people pulling on opposite ends of a rubber band. If Enceladus orbited in a perfect circle, it would settle into one stretched shape and stay that way, which would not generate much heat. But remember, Enceladus orbits in a slightly elliptical path. When Enceladus is closer to Saturn, the tidal stretching is stronger. When it moves farther away, the stretching is weaker. This means Enceladus is constantly being squeezed and relaxed over and over with each orbit. This flexing generates friction in the interior of the Moon, and friction generates heat. It is exactly like bending a wire coat hanger back and forth rapidly. The metal gets hot at the bend point because mechanical energy is being converted into heat energy through friction. This tidal heating is what keeps Enceladus's ocean liquid despite being so far from the Sun. The Sun provides almost no heat at Saturn's distance. Sunlight there is 100 times weaker than on Earth. If the Sun was Enceladus's only heat source, the Moon would be frozen to absolute zero. But tidal heating from Saturn provides enough energy to maintain a liquid ocean and power the geysers we see erupting from the surface. Now, here is where the story gets even more beautiful. Enceladus cannot maintain its elliptical orbit by itself. If Enceladus was alone, orbiting Saturn without any other moons nearby, its orbit would gradually become more and more circular due to tidal forces. A circular orbit would mean no more tidal flexing, no more heat, and the ocean would freeze. Enceladus would go dormant. But Enceladus is not alone. It shares space with dozens of other moons orbiting Saturn, and one of those moons, a larger moon named Dione, plays a crucial role in keeping Enceladus active. Dione orbits Saturn farther out than Enceladus, taking longer to complete each orbit. The two moons are locked in what scientists call an orbital resonance. Specifically, Enceladus completes exactly 2 orbits around Saturn for every 1 orbit that Dione completes. This means that every 2 orbits, Enceladus and Dione line up in the same relative positions. When they line up, Dione's gravity gives Enceladus a little gravitational tug, a gentle pull that prevents Enceladus's orbit from becoming circular. This resonance is stable, meaning it can persist for billions of years. Computer simulations show that once this kind of orbital configuration is established, it tends to maintain itself because the very gravitational interactions that created it also work to preserve it. As long as Dione is out there, pulling on Enceladus every 2 orbits, Enceladus will maintain its elliptical orbit. As long as the orbit stays elliptical, Saturn will continue to squeeze and flex Enceladus. As long as that flexing continues, tidal heating will keep the ocean liquid. The whole system is interconnected, each piece depending on the others. But the connection between Saturn and Enceladus goes even deeper. The plumes shooting from Enceladus do not just disappear into space. Some of the water vapor and ice particles spread out along Enceladus's orbital path, creating a faint ring around Saturn called the E-ring. This ring is invisible to the naked eye, but was detected by Voyager and studied extensively by Cassini. The E-ring extends from inside Enceladus's orbit all the way out beyond the orbit of another moon called Rhea, but it is densest right at Enceladus's orbital distance because that is where the source is. The material from Enceladus's plumes does not just stay in the E-ring forever. Over time, it can fall onto other moons, including Saturn's largest moon, Titan, coating them with a fine layer of ice particles from Enceladus's ocean. So, in a very real sense, Enceladus is sharing its ocean with the entire Saturn system. If we ever detect signs of life in Enceladus's plumes, we would need to consider whether that material could have contaminated other moons, spreading Enceladian microbes throughout the Saturn system. This possibility, called panspermia, is both exciting and complicating when we think about where life might exist. The Saturn system is not just a collection of independent objects. It is a family, a system where everything affects everything else through gravity, through orbital mechanics, through the exchange of material. Enceladus is active because of Dione, because of Saturn, because of the specific arrangement of orbits that has persisted for billions of years. Change any part of this system and Enceladus would be different. Remove Dione and the orbital resonance would break. Move Enceladus farther from Saturn and tidal forces would weaken. This finely balanced system has created one of the most remarkable environments in the solar system, and we are incredibly fortunate to be living at a time when we can study it. The discovery of an active ocean world on Enceladus did not just teach us about one moon. It fundamentally changed how scientists think about habitability in the universe. Before Cassini reached Saturn, the search for life beyond Earth was focused almost entirely on planets, specifically planets orbiting in what astronomers call the habitable zone of their star. Let me explain what this means and why Enceladus challenged this entire way of thinking. The habitable zone, sometimes called the Goldilocks zone, is the region around a star where temperatures are just right for liquid water to exist on a planet's surface. Not too hot, where water would boil away. Not too cold, where water would freeze solid. Just right, like the porridge in the Goldilocks story. For our Sun, Earth orbits right in the middle of this zone, which is why we have liquid oceans, lakes and rivers. Mars orbits near the outer edge of the habitable zone, which is why it is mostly frozen today, though it might have had liquid water in the past when it was warmer. Venus orbits near the inner edge, and it became too hot with all its water lost to space long ago. This concept of the habitable zone made perfect sense when scientists were only thinking about surface life like we have on Earth. Plants need sunlight for photosynthesis. Animals depend on plants or on other animals that ate plants. Everything on Earth's surface ultimately depends on energy from the sun. So the search for habitable worlds focused on finding planets at the right distance from their star, where the surface would be warm enough for liquid water but not too hot. But Enceladus completely breaks this framework. Enceladus orbits Saturn, which is 10 times farther from the Sun than Earth. At that distance, the sunlight is 100 times weaker. The surface of Enceladus is frozen to -200 degrees Celsius. By every definition of the traditional habitable zone concept, Enceladus should be completely uninhabitable. And yet, beneath its frozen surface, it has all the ingredients for life. Liquid water, organic molecules, energy from chemistry rather than sunlight. Enceladus does not care about the habitable zone around the Sun because it gets its energy from somewhere else entirely, from tidal heating powered by its parent planet. This realization forced scientists to expand their definition of habitability. It is not just about distance from a star anymore. It is about whether liquid water can exist anywhere, surface or subsurface. It is about whether an energy source is available, whether from a star or from gravitational tides or from radioactive decay or from any other process. It is about whether the right chemistry is present for life to build itself. The rules were rewritten. Suddenly, the number of potentially habitable places in the universe exploded. Before, scientists were only considering planets in narrow, habitable zones around stars. After Enceladus, they had to consider that almost any moon orbiting a giant planet could potentially be habitable if it experienced enough tidal heating. They had to consider that small icy bodies in the outer solar system might have hidden oceans. They had to think about habitability in a completely new way. This shift had profound implications for the search for extraterrestrial life. If habitable environments can exist so far from stars, in places we previously ignored, then life might be far more common in the universe than we thought. Every giant planet with moons became a potential host system for multiple habitable worlds. Every icy body became a candidate worth investigating. The universe suddenly seemed much more alive with possibilities. Think about the sheer numbers. In our solar system alone, we now know of several ocean worlds. Enceladus is one. Europa, Jupiter's moon, is another. Ganymede, also orbiting Jupiter, has an ocean. There is evidence for oceans on Callisto and Titan. That is, 5 confirmed or strongly suspected ocean worlds in just our one solar system. And our solar system is not special. There are billions of other star systems in our galaxy, many with giant planets, many of those giant planets likely having moons. If even a small fraction of those moons harbour subsurface oceans, we could be talking about billions of potentially habitable environments just in the Milky Way galaxy alone. Enceladus taught us that habitability is not rare. It is not confined to Earth-like planets in Earth-like orbits. It is common, it is diverse, and it exists in places we never thought to look. This is one of the most important paradigm shifts in the history of astrobiology, and it all started with a little white moon shooting water into space. Now that we understand how special Enceladus is, we need to talk about its bigger cousin, Europa. Europa is one of Jupiter's 4 largest moons, discovered by Galileo in 1610, and it has been fascinating scientists since the Voyager spacecraft first revealed its strange, cracked surface in the 1970s. In many ways, Europa and Enceladus are twins. Ocean worlds with remarkably similar environments despite orbiting different planets and existing at different locations in the solar system. But they also have important differences that make each one unique and interesting in its own way. Let us start with the similarities. Europa, like Enceladus, is covered in a shell of water ice. Beneath that ice, scientific evidence strongly suggests there is a vast liquid ocean, even larger than Enceladus's ocean. Europa's ocean is estimated to be 50 to 100 kilometers deep, much deeper than Enceladus's 10-kilometer deep ocean. And because Europa is larger than Enceladus, the total volume of water in Europa's ocean might be 2 to 3 times the volume of all of Earth's oceans combined. Think about that. One moon orbiting Jupiter contains more water than our entire planet. Like Enceladus, Europa gets its energy from tidal heating. Jupiter is even more massive than Saturn, and Europa orbits closer to Jupiter than Enceladus orbits to Saturn, which means the tidal forces Europa experiences are even stronger. Europa is locked in an orbital resonance with 2 other Jovian moons, Io and Ganymede, which keeps its orbit slightly elliptical and maintains the tidal flexing that generates heat. So the same basic mechanism that powers Enceladus is powering Europa. The surface of Europa is fascinating and bizarre. It is crisscrossed with countless dark streaks and cracks called lineae, giving it the appearance of a cracked eggshell. Some areas show what scientists call chaos terrain, where the ice appears to have broken apart, moved around, and refrozen in jumbled patterns. These features suggest that the ice shell is active, that material from below sometimes breaks through, and that the surface gets reprocessed over time, though not as dramatically as on Enceladus. Europa's surface is older than Enceladus's, with more craters, suggesting resurfacing happens more slowly there. But here is where Europa and Enceladus differ in a crucial way. Enceladus makes our job easy by shooting its ocean water directly into space where we can sample it. Europa does not do this. There have been some observations suggesting that Europa might occasionally have plumes similar to Enceladus, but these are rare, intermittent, and much less dramatic. For the most part, Europa keeps its ocean secret beneath a thick shell of ice that scientists estimate is 15 to 25 kilometers thick, possibly even thicker in some places. This creates a major challenge for exploring Europa. On Enceladus, we can fly through the plumes and directly sample ocean water without ever landing. On Europa, we would probably need to send a lander that could drill or melt through 15 or more kilometers of ice to reach the ocean. This is not impossible, but it is technologically difficult and expensive. Ice is hard. Drilling through it takes time and energy. We would need to develop completely new technologies, power systems that could run for weeks or months while the drill slowly melts its way down, communication systems that could relay data through kilometers of ice back to a surface relay station. Despite this challenge, Europa remains one of the highest priority targets in the search for life beyond Earth. Its ocean is larger and possibly older than Enceladus's ocean. Scientists have evidence suggesting Europa has hydrothermal vents on its ocean floor, just like Enceladus probably does, and Earth definitely does. The ice shell might actually be an advantage in some ways because it provides protection from radiation. Jupiter's radiation environment is brutal, far worse than Saturn's, and any life on Europa's surface would be killed by it. But life deep in the ocean would be shielded by all that ice, protected from radiation while having access to everything it needs. NASA is currently developing a mission called Europa Clipper, scheduled to launch in 2024 and arrive at Jupiter in 2030. This spacecraft will not land on Europa, but will perform multiple close flybys, studying the Moon with radar to probe the thickness of the ice, analyzing the composition of the surface, looking for plumes if they exist, and mapping the entire Moon in high resolution. The European Space Agency is also sending a mission called JUICE that will study Jupiter's icy moons, including Europa. These missions will give us our best look yet at this mysterious ocean world. In the friendly rivalry between Europa and Enceladus fans, both moons have strong cases. Europa is bigger, might have more liquid water, and might have had more time for life to evolve. Enceladus is more active, more accessible for sampling, and has already given us incredible data about its ocean chemistry. Some scientists argue we should focus on Europa because of its size and age. Others argue Enceladus is the better target because we can study it more easily without needing to drill through ice. Personally, I think the answer is both. We should explore both worlds because they might teach us different things about how ocean worlds work and whether life can emerge in these hidden seas. Europa and Enceladus are the two most famous ocean worlds, but they are far from the only ones. In fact, as scientists have gotten better at detecting subsurface oceans using gravity measurements, magnetic field data and geological evidence, they have realized that ocean worlds might be the most common type of habitable environment in the solar system. Let me take you on a quick tour of the other known and suspected ocean worlds in our cosmic neighborhood. Starting with the Jupiter system, we have Ganymede, the largest moon in the entire solar system, even bigger than the planet Mercury. Ganymede has a weak magnetic field, which is unusual for a moon, and studies have shown this magnetic field interacts with Jupiter's magnetic field in ways that suggest there is a salty ocean beneath Ganymede's surface. probably about 100 to 200 kilometers down, beneath multiple layers of different types of ice. This ocean might be sandwiched between layers of ice, with regular ice on top and high-pressure ice below, creating a bizarre, layered structure unlike anything on Earth. Whether life could exist in such a compartmentalized ocean remains an open question. Next is Callisto, another large Jovian moon. Callisto looks dead from the outside, heavily cratered with ancient terrain, but gravity measurements and magnetic data suggest it too might harbour a subsurface ocean, possibly 100 or more kilometres down. Callisto's ocean would be cold and isolated, with little energy input compared to more active moons. But liquid water is liquid water, and where there is water, there might be life, even if that life exists in a low-energy, slow-motion environment. Moving to Saturn, we have Titan, Saturn's largest moon and one of the most bizarre places in the solar system. Titan has a thick atmosphere, lakes and rivers of liquid methane and ethane on its surface, and beneath its icy crust, scientists believe there is a subsurface ocean of liquid water mixed with ammonia. This ocean would be very different from Enceladus's ocean, colder, more ammonia-rich, but still potentially habitable. Titan is fascinating because it might actually have two kinds of potential habitability, one in the subsurface water ocean and another in the surface methane lakes, where completely different chemistry could support methane-based life, if such a thing is possible. Even tiny Mimas, another Saturn moon, only about 400 kilometers across, recently surprised scientists with evidence of a subsurface ocean discovered through careful analysis of its orbital wobble. Mimas looks completely dead from the outside, heavily cratered with no signs of geological activity, yet beneath that ancient surface there might be an ocean. If Mimas has an ocean, it suggests that subsurface oceans might exist on even more moons than we realized, hiding beneath perfectly normal-looking icy surfaces with no surface clues to give them away. Venturing out to the Neptune system, we find Triton, Neptune's largest moon and one of the coldest surfaces in the solar system. Triton is strange because it orbits Neptune backward compared to the planet's rotation, suggesting it was captured from the Kuiper belt rather than forming alongside Neptune. Despite its frigid surface, Triton shows signs of geological activity. Voyager. Two photographed geysers erupting from Triton's surface in 1989, though these were probably nitrogen geysers rather than water. Still, the geological activity suggests internal heat, and where there is heat, there might be liquid water somewhere deep inside. Even in the asteroid belt between Mars and Jupiter, there might be ocean worlds. The dwarf planet Ceres, the largest object in the asteroid belt, shows evidence of water ice and possibly briny liquid beneath its surface. Some craters on Ceres have bright white deposits that might be salt left behind when subsurface brines percolated up and evaporated. The pattern that emerges from all these discoveries is clear. Ocean worlds are not rare exceptions. They are common features of the outer solar system. Almost any icy body large enough to maintain internal heat and small enough to avoid becoming too geologically complex seems capable of harbouring a subsurface ocean. Some of these oceans are more accessible and potentially habitable than others, but they are all there, hidden beneath ice, waiting to be explored. This raises a profound question. If ocean worlds are this common in our solar system, how common are they in other star systems? Every star system we have studied that has giant planets seems to have moons. If those moons are similar to our solar system's moons, then ocean worlds might exist around billions of stars throughout the galaxy. The universe might be full of hidden oceans, each one a potential harbour for life. Enceladus did not just teach us about one moon. It opened our eyes to an entire class of worlds that might be among the most common habitable environments in the cosmos. Let us step back for a moment from the scientific details and think about what all of this means. The discovery of ocean worlds throughout our solar system has implications that go far beyond science. It touches on philosophy, on our place in the universe, on the very question of what it means to be alive in this cosmos. For thousands of years, humans believed Earth was the center of everything. The sun and stars revolved around us. We were special, unique, the whole point of creation. Then Copernicus and Galileo showed us that Earth is just one planet among several orbiting the sun. Our specialness diminished. Then we discovered that the sun is just one star among billions in our galaxy, and our galaxy is just one among billions of galaxies. Our specialness diminished further. Each discovery made us seem smaller, less significant, more ordinary in the grand scheme. The discovery of ocean worlds continues this trend of humbling humanity, but it also does something else. It shows us that the universe is far more hospitable to life than we thought. We used to think habitable environments were rare, limited to planets like Earth in narrow zones around sun-like stars. We thought we might be alone, or nearly alone, the only intelligence in a cold, dead cosmos. But now we know that hidden oceans exist throughout our own solar system. We know that the ingredients for life, water and organic molecules and energy, are common rather than rare. If life exists on Enceladus or Europa or any of the other ocean worlds, it would be the most profound discovery in human history. It would mean life has emerged at least twice in our solar system, independently on Earth and independently on one of these moons. And if life has emerged twice in just our one solar system, the statistical implications are staggering. It would suggest that life emerges wherever conditions allow, that the universe is not just capable of producing life, but does so frequently, perhaps inevitably, given the right circumstances. Think about what that would mean. We would not be alone. We would be part of a living universe, a cosmos teeming with life in hidden places, life that never sees stars, life that exists in eternal darkness powered by chemistry and heat. Some of that life might still be microbial, simple, primitive. But given billions of years, could some of it evolve into something more? Could intelligence emerge in an ocean world? Could civilizations develop in the dark? These questions move from science into speculation, but they are questions worth asking because the discovery of even simple life elsewhere would tell us that the path from chemistry to biology is not impossibly rare. On the other hand, if we thoroughly explore multiple ocean worlds and find them all lifeless, that would also teach us something profound. It would tell us that having the right ingredients is not enough. It would tell us that the emergence of life requires something more, some additional factor we do not yet understand, some stroke of luck or perfect alignment of circumstances that might be extraordinarily rare. Finding sterile oceans on world after world would make Earth seem more precious, more unique, more deserving of our protection, because life might be the rarest thing in the cosmos. Either answer changes everything. Either we live in a universe full of life, or we live in a universe where life is so rare that we might be effectively alone. Enceladus and its sister ocean worlds hold the key to answering this question. They are natural laboratories where we can test our theories about life's origins. They are windows into processes that might be happening throughout the galaxy. They are, quite possibly, the most important places we could explore if we want to understand our own existence and place in the universe. This is why scientists get so excited about Enceladus. It is not just about one moon, it is about answering the oldest question humanity has ever asked. Are we alone? For the first time in history, we have the technology and knowledge to actually answer that question. We just need to go back, to look more carefully, to search with purpose and precision. The answer is waiting there, in the dark ocean beneath the ice, waiting for us to find it. So we have established that Enceladus has all the ingredients for life. We know it has liquid water, organic molecules, and an energy source. We know its ocean has been liquid for potentially billions of years, giving life time to emerge and evolve. The question now is, how do we actually detect life if it exists there? This is not as simple as it sounds, and it requires us to think carefully about what life actually is and what signs it leaves behind. On Earth, detecting life is easy. You just look around. There are plants, animals, fungi, bacteria everywhere. Even if you go to the most extreme environment on Earth, the driest desert, or the coldest glacier, or the deepest ocean trench, if you bring back a sample and look at it under a microscope, you will almost certainly find living cells. Earth is teeming with life, to such an extent that the hard part is finding places where life does not exist. But on Enceladus, we cannot just look around. We are studying it from billions of kilometers away. Even if we send another spacecraft, it will be a robot with limited instruments, not a trained biologist with a full laboratory. We need ways to detect life remotely, through chemical signatures or physical signs that living organisms produce. Scientists call these signs biosignatures. What would a biosignature look like? On Earth, life leaves many distinct marks. Living organisms alter their environment in ways that are different from non-living chemistry. They produce specific molecules that do not form easily without biological help. They create patterns and structures that reflect biological organization. They leave behind chemical imbalances, places where there is too much or too little of certain elements compared to what pure chemistry would produce. For example, Earth's atmosphere contains 21% oxygen. This much oxygen should not exist because oxygen is chemically reactive and should combine with other elements in rocks and oceans. The only reason we have so much atmospheric oxygen is because plants produce it through photosynthesis faster than chemistry can remove it. The oxygen in our atmosphere is a biosignature, a sign that photosynthetic life is present. If aliens were studying Earth from far away, they would see our oxygen-rich atmosphere and know immediately that something biological must be happening. On Enceladus, we cannot look for oxygen because any life there would not be photosynthetic. But we can look for other chemical imbalances. For instance, if we found methane and carbon dioxide and hydrogen in ratios that do not make thermodynamic sense, ratios that suggest something is actively producing or consuming these gases faster than chemistry alone would, that could be a biosignature. If we found complex organic molecules that have specific handedness, meaning their molecular structure is predominantly left-handed or right-handed rather than a random mix, that could indicate biological synthesis because life on Earth preferentially makes molecules with specific orientations. Another approach would be looking for patterns in the organic molecules. Life uses a limited set of organic molecules, even though many more types are possible. If we found that Enceladus's ocean contained very specific organic compounds in much higher abundance than others, compounds that match what Earth life uses like amino acids in specific configurations, or nucleotides that make up DNA, that would be suspicious and might indicate biology. We could also look for cells themselves. This would require more advanced instruments than Cassini carried. We would need microscopes capable of imaging particles in the plume samples. We would need to look for objects that are the right size to be cells, that have membranes enclosing contents, that perhaps show internal structure. Finding even one definitive cell in a plume sample would be absolute proof of life. The challenge is that all of these biosignatures can potentially be mimicked by non-biological processes. Chemical imbalances can be produced by unusual geology. Organic molecules can be synthesized abiotically. Patterns can emerge from chemistry without biology. This means we cannot rely on a single measurement. We would need multiple independent lines of evidence, all pointing toward biology before scientists would be convinced. Current instruments are simply not sensitive enough to make these measurements conclusively. Cassini gave us incredible data about Enceladus, but it was not designed specifically to search for life. Its instruments could detect broad categories of organic molecules, but could not identify specific compounds or measure their detailed properties. It could count ice grains, but could not see cellular-level structures. To truly search for life on Enceladus, we need a new mission, purpose-built with advanced instruments specifically designed to look for biosignatures. And that mission is being planned. The scientific community is actively advocating for a return mission to Enceladus, and several concepts have been proposed and studied. The most prominent proposal is called the Enceladus Orbilander, a mission that would both orbit Enceladus for extended studies and eventually land on the surface near the tiger stripes. Let me describe what this mission would do and why it would be so exciting. The Orbilander concept envisions a spacecraft that arrives at Saturn and enters orbit specifically around Enceladus rather than Saturn itself. This is technically challenging because Enceladus is small and does not have strong gravity, but it would allow the spacecraft to fly through the plumes dozens or even hundreds of times, collecting multiple samples over months or years. Each pass through the plumes would give scientists more data, more ice grains to analyze, more chances to detect biosignatures if they exist. The spacecraft would carry advanced instruments far more sophisticated than Cassini's. These would include high-resolution mass spectrometers that could identify specific organic molecules rather than just detecting their general presence. It would have instruments capable of measuring the chirality of molecules, their handedness, to look for biological preferences. It would have microscopes that could image individual ice grains at high magnification to look for cell-like structures. It would have instruments to analyze isotope ratios, the relative abundance of different versions of atoms, because life often preferentially uses certain isotopes. After conducting orbital studies, the spacecraft would attempt to land on Enceladus near the South Polar region, possibly on one of the tiger stripes themselves or nearby, where plume material frequently rains down. The lander would carry additional instruments to study the surface composition, measure the heat flow from below, perhaps even drill a short distance into the ice to collect subsurface samples. Landing on an active geyser field would be challenging and potentially dangerous, with the risk of ice particles damaging the lander, but it would also provide the most direct access to fresh ocean material. The timeline for such a mission is frustrating for those of us eager to find answers. Designing, building and testing a mission like Orbilander takes at least a decade. Then there is the travel time to Saturn, another 6 to 8 years. So if a mission was approved today, we would not get results until the late 2030s at the earliest, possibly the 2040s. That is a long time to wait, but space exploration requires patience. There are also more ambitious concepts being discussed for the more distant future. Some scientists have proposed eventually sending a cryobot, a probe that could melt through the ice shell and deploy a small submarine into Enceladus's ocean. This sounds like science fiction, but the technology is actually being developed. Engineers have tested cryobots in Earth's Arctic and Antarctic ice. The basic idea is simple. The probe generates heat, melts the ice directly in front of it, and slowly descends through the meltwater while trailing a communication cable back to the surface. The challenges of a cryobot mission to Enceladus are immense. It would need to melt through 20 to 30 kilometers of ice, which would take months or even years. It would need a power source that could run for that long, probably a nuclear battery. It would need to avoid getting stuck if the ice refreezes around it. Once it reached the ocean, the submarine would need to operate autonomously, because communication delays of hours make real-time control impossible. It would need to navigate in complete darkness, avoid obstacles, and find interesting features to study, all on its own. Despite these challenges, A cryobot mission is the dream for many scientists because it would give us direct access to the ocean. We could sample the water directly, image the ocean floor with sonar, look for hydrothermal vents, search for life in its natural habitat rather than studying material that has been blasted through kilometers of ice into space. This kind of mission probably will not happen for many decades, but it represents the ultimate goal of Enceladus exploration. NASA and other space agencies must prioritize among many worthy targets. Europa is also a high priority and is getting the Europa Clipper mission. Mars continues to be studied for signs of ancient life. The outer ice giants Uranus and Neptune have never had dedicated orbital missions and deserve attention. Venus, surprisingly, might have habitable conditions in its upper atmosphere and is gaining interest. Titan is fascinating for many reasons, so Enceladus must compete for funding and attention with all these other worthy destinations. But I believe Enceladus deserves to be a top priority. It gives us free samples of its ocean. It shows clear evidence of current geological activity. It has all the ingredients for life, and it is accessible with current technology. We do not need to develop revolutionary new systems to explore Enceladus. We just need the will to do it and the funding to make it happen. The science return would be extraordinary, potentially answering the question of whether life exists beyond Earth. What could be more important than that? You might be wondering why we should spend billions of dollars and decades of effort to explore a tiny moon orbiting Saturn. After all, Earth has plenty of problems that need solving. We have poverty, disease, climate change, conflicts, and so many challenges that demand attention and resources. Why should we care about life on a distant ice moon when there are urgent needs right here at home? This is a fair question, and it deserves a thoughtful answer. The exploration of Enceladus and the search for life beyond Earth matters for many reasons, some practical and some philosophical, but all important. First, the practical reasons. Space exploration drives technological innovation in ways that benefit life on Earth. The Apollo program, designed to land humans on the moon, produced thousands of spin-off technologies that we use today. Medical imaging devices, computer miniaturization, water purification systems, improved materials, satellite communications, GPS navigation, all trace their lineage back to space technology. Developing the advanced instruments needed to search for life on Enceladus will similarly produce innovations in chemistry, microscopy, robotics, artificial intelligence, power generation, and data analysis. These technologies will find applications in medicine, environmental monitoring, manufacturing, and countless other fields. Second, studying other ocean worlds teaches us about Earth. Enceladus and Europa are natural laboratories where we can observe geological and chemical processes in environments different from Earth, but still comparable. Understanding how oceans work on other worlds, how ice shelves behave, how tidal heating operates, all feeds back into our understanding of Earth's own systems. Climate scientists study other planets to understand climate. Oceanographers study other oceans to understand our oceans. Knowledge gained from space exploration makes us better stewards of our own planet. Third, and most importantly, the search for life beyond Earth addresses fundamental questions about existence. Where did we come from? How did life begin? Are we alone? These are questions humans have asked since we first looked up at the stars and wondered. For most of history, these questions belonged to philosophy and religion because we had no way to empirically answer them. But now, for the first time in human history, we have the tools and knowledge to potentially answer these questions through observation and experiment. If we find life on Enceladus, even simple microbial life, it would be the most profound discovery in the history of science. It would tell us that life is common in the universe, that wherever conditions permit, life emerges. It would mean we are not alone, that the universe is a living place, full of other organisms experiencing their own existence in their own environments. It would raise new questions about whether some of that life has evolved intelligence, whether we might someday communicate with alien minds, whether the universe is full of civilizations and cultures and philosophies completely different from our own. If we thoroughly explore Enceladus and find no life despite all the right conditions being present, that would also be profound. It would tell us that life is difficult, rare, special. It would make us appreciate Earth more. It would tell us that we have a responsibility to protect and cherish the life on our planet, because it might be extraordinarily uncommon in the cosmos. Either answer, life or no life, teaches us something fundamental about reality. There is also an inspirational value to space exploration that should not be dismissed. Missions like Cassini inspire young people to study science and engineering. They unite humanity around a common goal that transcends national boundaries and political differences. They remind us that we are capable of incredible achievements when we work together toward ambitious objectives. The images from Enceladus, the story of its hidden ocean, the possibility of life in that ocean, all of this captures the imagination and reminds us that we live in a universe full of wonder and mystery. Finally, exploration is simply part of human nature. We explore because we are curious, because we want to know what is over the next hill, across the next ocean, around the next planet. We explore because the unknown calls to us, because we are not content with ignorance, because we believe understanding is valuable for its own sake. The exploration of Enceladus continues a tradition that goes back to the first humans who walked out of Africa to see what lay beyond. The first sailors who crossed oceans not knowing what they would find. The first astronomers who pointed telescopes at the sky to see worlds no human eye had seen before. We explore Enceladus for the same reason we have always explored. Because it is there, because it is possible, and because not exploring would mean accepting ignorance when knowledge is within our reach. We have come a long way together in this story. We started with those spectacular images of water shooting 500 kilometers into space from a moon that should have been frozen dead. We followed the detective work of scientists piecing together clues from plume samples, gravity measurements, and chemical analysis. We learned about tiger stripes and tidal heating and orbital resonances. We discovered that this tiny moon harbors a global ocean that has been liquid for potentially billions of years. We found that this ocean contains all the ingredients life needs: water, organic molecules, and energy. Enceladus forced us to rewrite the rules about habitability. It taught us that ocean worlds are common throughout the solar system and probably throughout the universe. It showed us that life does not need sunlight or an Earth-like planet or any connection to a surface world. Life just needs the right chemistry and enough time. This tiny moon, barely larger than a few hundred kilometers across, has expanded our understanding of where and how life might exist in this cosmos. But despite everything we have learned, the biggest question remains unanswered. Is there actually life in that hidden ocean? Are there microbes clinging to rocks on the seafloor, metabolizing hydrogen and exhaling methane? Are there communities of organisms surrounding hydrothermal vents, living in total darkness, completely unaware that stars exist or that humans on a distant rocky planet are wondering about them? Or is that ocean empty, sterile, chemically rich, but biologically dead, despite having everything needed for life to begin? We do not know yet, and that not knowing is both frustrating and exhilarating. It means the answer is still out there, waiting to be discovered. Those geysers shooting into space are like Enceladus calling to us, saying, "Here is my ocean, come and see what I'm hiding, come and learn my secrets." The plumes are an invitation, perhaps the most important invitation humanity has ever received. Every time Enceladus erupts, every time water sprays upward from those tiger stripes, that water contains information about what lies below. Each ice grain is a message from the deep ocean, carrying molecules and chemicals that tell the story of what is happening in that dark, cold, hidden sea. We collected some of those messages with Cassini. We analyzed them. We learned incredible things. But we did not learn everything. We did not have the right instruments to detect subtle biosignatures. We did not look carefully enough or long enough. We got a glimpse, but not the full picture. That is why we need to go back. We need to send a new mission with better instruments. We need to fly through those plumes again and again, collecting samples, analyzing them with precision, looking specifically for signs of life. We need to orbit Enceladus for years, mapping every detail, understanding every aspect of this ocean world. And eventually, someday, we need to land there, to drill down, to send probes into that ocean and see what is really there. The answer is waiting for us. It is there beneath 20 kilometers of ice, 1.4 billion kilometers from Earth, orbiting a ringed giant planet at the edge of the solar system's habitable zone. It has been waiting for billions of years, long before humans existed, long before Earth had complex life, long before the dinosaurs or the mammals or anything more complicated than microbes. That answer has been patient. It can wait a few more decades while we prepare ourselves to discover it. But make no mistake, that answer exists. Either life is there or it is not. Either Enceladus's ocean teems with microbes or it is sterile. Either we are about to discover that the universe is full of life, or we are about to learn just how special and rare Earth truly is. Either way, the answer will change how we see ourselves, how we understand our place in the cosmos, how we think about the meaning of existence. Enceladus is calling. The plumes are shooting upward, carrying their messages, waiting for us to listen more carefully. The ocean is there, hidden but not unreachable, mysterious but not unknowable. We have the technology. We have the knowledge. We just need the determination to go and look. The most mysterious moon in the solar system is not going to stay mysterious forever. Its secrets will be revealed. The only question is whether our generation will be the one to reveal them, whether we will be the people who finally answer the question that has haunted humanity since we first looked up at the night sky and wondered if we were alone. The geysers are waiting. The ocean is waiting. The answer, whatever it is waiting. And now, so are we.